We're on lesson 65 now. This is applications using similar triangles, and we've got our objective here, so let's get started with the problem. It says, Mary Cruz wants to know the height of a flagpole. She stands a meter stick in a vertical position and finds the length of the shadow is 120 centimeters. At the same time, the shadow of the flagpole is 30 meters long, and we want to know how tall is the flagpole. Okay, now you might be asking yourself, why would Mary Cruz, if she wants to know the height of the flagpole, why would she measure its shadow and then stand a meter stick in the ground and measure its shadow? Well, it's not very logical of us to think that Mary Cruz could take like a measuring tape and climb herself up the flagpole to see how tall it is. Okay, so she's got this idea of something she might have learned in math class, and we're going to use similar triangles to solve this. Okay, so what happens is if we think about this, here's our meter stick, and they change it to 100 centimeters, okay, because that's how much 1 meter is. And the reason why they changed it is because the shadow was measured in centimeters. So we want to keep these measurements the same. Alright, so if we look at this, here's our meter stick, and it's 100 centimeters tall. And it's got a shadow that's 120 centimeters. Okay, so we'll pretend like the sun's up here, shining down. Okay, and if you look at this, we could make this like a triangle. Alright, and with the flagpole we could do the same thing. Here's the flagpole, here's its shadow, 30 meters, and we want to know how tall is this, and we want to keep the measurements the same. Okay, so if the flagpole's shadow is in meters, we want to know how many meters tall this flagpole is. And again, we could connect this and make a triangle. Now again, the reason why Mary Cruz wants to use the meter stick method and measure the shadows is because using math we can now solve for how tall this flagpole is. What we're going to do is we're going to set up a ratio box. Okay, we're comparing two things here, the meter stick to the flagpole. And for the meter stick, we're looking at two things. We're looking at the height of the meter stick and the length of its shadow. And same thing for the flagpole. We're looking at the height and the length of its shadow. So we're going to also compare the height of each object and the shadow of each object. And now I'm going to fill in what we know. We know that the meter stick's height is 100 centimeters. And we know that the length of the meter stick's shadow is 120 centimeters. Then we don't know the height of the flagpole, but we know the length of its shadow, which is 30 meters. Okay? Now we're just going to go ahead and use the numbers they gave us, even though one's in meters and the other two are in centimeters, to solve this. And when we answer this, we know that our flagpole shadow was labeled meters, so we're going to have meters as our answer. Now again, the nice thing about this is using math on this problem, we can now set up a proportion for this. Sorry, I don't know what happened to the rest of that, but we'll go ahead and solve it. Okay, so we're going to put 100 over 120 is equal to x over 30. Okay, now using cross products, we get 120 times x equals 30 times 100. Well, 1 times 3 is 3. And then there's 1, 2, 3 zeros, so that's 3,000. Now I'm going to solve this by solving for x. And if I take 3,000 divided by 120, I'm going to get 25. Okay, and we can show that math right here real fast. Okay, we can knock off one of the zeros on the end, so like we're doing 12 into 300, and 12 goes into 30 twice. If I multiply, I get 24, and subtract, and get 6, and bring down a 0, and 12 goes into 65 times. Okay, so we get 25 for our x value. So now we need to answer the question. The question said, how tall is the flagpole? So we're going to say the flagpole is 25, and again, it was in meters tall. Again, the reason why Mary Cruz wanted to do this experiment with the meter stick and the shadows is because it's going to be tough for her to measure something that's 25 meters tall. Okay? That would be like probably about 75 feet or somewhere in there. So that's not reasonable for her to do. So she was curious about the height of the flagpole. We can use math to solve this using similar triangles. Alright, and let's do one more example. Okay, here we got a pretty lengthy word problem. Now this one is another example of a time when it would not be possible for you to measure something. Okay, and again, this is called indirect measurement. When we don't know something directly, so we cannot, in that last one, we couldn't directly measure the height of the flagpole. We couldn't put like a big stick of some sort up against the flagpole and measure all the way up it, okay, or use a tape measure and go all the way up the flagpole. So Mary Cruz indirectly measured it. So here's another example of that. It says Josh stood facing a pond. Okay, so here's Josh, and here's the pond over here. From his viewpoint, he could see 2 points on opposite sides of the pond. So he can see this point called P1 and this point called P2. Okay, so they might be different docks on the pond, maybe. So if he stands here, he looks, he can see the dock over here and the dock up over here on opposite sides. And he wanted to know the distance between those two because that would tell him the distance across the lake. But he doesn't have a way to measure that directly. Okay, because again, he can't take a big piece of tape measure and pull it clear across the lake. That's not logical. So he had an idea. It says he can indirectly measure the distance. So what he did is he marked his spot with a stone. Okay, so we put a stone in the ground right here. And then he walked 10 yards toward point 1. Okay, so he went this way 10 yards and put a stake into the ground. Okay? Then what he did is he tied a piece of string to the stake and stretched it out so that it went parallel to these points, or to the distance across the lake. Okay, so he took his piece of string and just stretched it out this way as far as it would go. Okay? Then what he did is he returned to his starting spot and he walked in a line from himself to the piece of string that would continue toward point 2. Alright? And when he reached the string, he drove another stake into the ground and tied the string around it. Okay, so basically what we got here is we got a stake in the ground and a stake in the ground with a piece of string tied to him. Okay? And if Josh walked in a straight line from himself, the stone that he had, to the stake, and he continued that straight line, he would hit the dock over here. And likewise, if he started at his stone and walked toward his second stake and kept going in a straight line, he could walk straight to the dock up here. And he knows that the distance from his starting position to the first dock is 45 yards. Okay? And then it says if the distance between the first stake and the second stake is 8 yards, then we want to know what the distance across the pond is. Okay, so let's draw this. See how they drew this picture? And it looks like there's a little triangle here and then a bigger triangle here. Let's go ahead and look at those two triangles. So here's our little triangle, and then here's our big triangle. Okay, in both of these cases, here's Josh over here. Then up here we've got the point 2 and the point 1. And on the little drawing, we've got the first stake and the second stake. Okay, so let's fill in what we know here. It says right here, I'm looking for numbers throughout all this stuff that we can fill in. Okay, so here I see one that says 10 yards. So we need to figure out where in our two drawings that would go. It says that he started at the large stone and walked 10 yards toward point 1 and put his stake in the ground. So this is the distance between Josh and his first stake. So that's 10 yards. Okay, now let's read through all this stuff and look for another number. Okay, here I see 45 yards. This says that Josh knew the distance from his starting position to P1 is 45 yards. So that's his starting spot to point 1, the dock 1. So that's 45 yards. That goes on the big triangle. Then it says the distance between the first stake and the second stake ended up being 8 yards. So that's how long the string was here. So this right here is 8 yards. Okay? So I'm going to go ahead and put 8 yards right here. And then we want to know the distance from P1 to P2. So I'm trying to figure out this right here. Okay, so now if I could redraw these two triangles with just the numbers, I've got a small triangle here. It's got 10 here and 8 here. And then I've got a bigger triangle that's got 45 here and x here. I don't know that. So again, we're going to use our application of similar triangles to do this. So we can make another ratio box here using these two triangles. Okay, so I'm going to have the small triangle and the big triangle. Okay, and I'm able to compare the bottom sides and the up and down sides, the heights. Okay, so I'm going to compare the base of the triangle and the height of the triangles. Well, the base of the small triangle is 10, and the height of the small triangle is 8, and the base of the big triangle is 45, and then we want to know the distance across the pond here, the height of this triangle, in yards. So I'm going to set up a proportion and solve this. So I'm going to have 10 over 8 equals 45 over x, and use cross products to solve. Okay, so I'm going to have 45 times 8, and 8 times 5 is 40, carry the 4. 8 times 4 is 32, plus 4 is 36, so that's 360, equals 10 times x. So then I'm going to divide by 10 on both sides, and 360 divided by 10 gives me x equals 36. So now my answer to the question is the distance is how many yards. So it's going to be 36 yards across that pond. Again, using our applications of similar triangles. Alright, that's your notes for the lesson. Good luck on the homework.